Huh. Hello everyone, very good evening. I welcome you all at PW, and today we are going to have the second session of the chapter Set Theory and Algebra of Discrete Mathematics. Okay, so what are we going to learn in this particular chapter or in this particular session? So we in the last class we have already discussed the concept related to set, that what do we mean by set, what are the different ways in which a set can be represented. Apart from that, what are the different types of set: empty set, equal set, equivalent set, finite set, infinite set, universal set, subset, superset, power set. Various types of sets we have discussed in the last class. Now and today we will try to understand that on sets, what are the different types of operations which can be performed, and what are the properties which are followed by the set operations. That is, if you perform two set operations, then what are the properties that will hold true during those set operations. Apart from that, we'll try to understand the concept of Cartesian product, that how do we perform the Cartesian product of two different sets, and what does it actually represent. Apart from that, we will try to understand the different types of relations, that what are the different types of relations which are possible from one set to another set or on the same set. So these are the different things which we are going to discuss in the today's session. In the last session, I gave you a homework problem. This is the homework problem, that let PS denote the power set of a set S. So there is a set S, whatever the set is, and there is a power set of that given set. Now, which of the following is always true? Please try to understand why did I give you this problem. Because this is actually a gate problem. The options are also which were available in the question paper of gate exam, but ultimately none of them is true. So if you come across this problem ever when you are trying to solve the question, then you should not get confused. Therefore, I have included this particular problem in the session, and I gave you this problem as a homework so that you can understand more about this particular problem. So let's discuss. So PS is the power set of set S. Now it is saying that power set of a set S, will be, so this is RHS, power set of a set S will be equals to power set of set S. Will it be true? No, sir, because the cardinality of power set of S will be more than the cardinality of power set of S. You can eventually understand that. Let's assume, if I take a simplest example, just let's assume that S is phi. Let's assume that S is phi. Then what will be power set of S? Sir, power set of S, yesterday we discussed that power set of S will be nothing but a set containing the subsets of set S. But if set itself is an empty set, then the only subset of an empty set will be phi itself. So either you can represent it like this, or you can represent it like it is a set and the element of this set will be an empty set, that is set S itself, because there is only one subset of phi. So this is power set of S. If you look at this, what is the cardinality of power set of S? The cardinality of power set of S is 1. What is the cardinality of S? Cardinality of S is 0. Now if you try to calculate power set of S, power set of S, then what does it mean? Sir, power set of S will be a set. And what will be the elements of this power set? What will be the element of this set? Sir, power set of S will be a set, and the elements will be nothing but the subsets of power set of S. Subsets of power set of S, because we are passing the power set of S as an argument to this particular function which is power set. Now, what are the subsets of power set of S? Please, sir, power set of S is this set. Sir, there is the cardinality of power set of S is 1. There is one element. Okay. So what are the subsets of power set of S? So the subsets of power set of S will be nothing, because the cardinality is 1. Please try to understand, whenever the cardinality is 1, let's assume that there is only one element. So what are the subsets of A? What are the subsets of A? So subsets of A will be, one subset will be phi, another subset will be set itself. Similarly, now if the cardinality of power set of S is 1, then ultimately there will be two subsets of this set. One will be an empty set and another will be this power set of S itself. Clear? Now you may think, just tell me whether this are two different elements or same elements. So this is different, these two are not equal. These two are not equal. So there are two elements in this particular set. So you can actually see that power set of S is not equal to power set of S. So this one is false. Again, if you take the intersection of power set of S with power set of S, they are trying to say that this will come out as phi. They are trying to say that this will come out as phi. True or false? That if you take the intersection of power set of S and power set of S, then this will be a set containing element phi. Power set of S will be this, that is a set containing element phi, and power set of S will be this. So phi will be an element of power set of S, absolutely fine. Phi an element of power set of S. Always true. Power set of S is this. Yes, sir. And again, one subset will be phi. Absolutely fine. But is it necessary? So come on, let's try to understand. Sir, if you look at this particular example, then you will realize that, sir, power set of S is a set containing element phi, and power set of S is a set containing element phi, and apart from that there is another set which contains element phi. If you take the intersection, then this will come out as phi. If you take the intersection, then this will come out as phi. So in general, you will think that this statement is true, but it says that whether it will be always true or not. Will it be always true? Come on, let's try to understand that this will always be true or not. So let's look at the another example, and that's why I give this problem as an homework problem. Please try to understand that. Let's assume my set S. Assume my set S is an set containing element 1 and this. These are two distinct elements. I hope you understand that these are two distinct elements. Yes, sir, these are two distinct elements. One is element 1, another is a set containing element 1. Now, if I define power set of S, sir, what will be power set of S? Sir, power set of S will be an empty set, a set containing element 1. Wait a minute, you will get this. A set containing element 1. Apart from that, a set containing another element, and another element is a set containing element 1. Apart from that, the next one will be 1, comma 1. What the idea? This will be power set of S. Now, if we look at power set of S, so what will be power set of S? Guaranteed. One thing is that, sir, one element will be phi. One element will be phi. Apart from that, sir, another element will be set containing element 1. This is one element, this. Clear? Now, please try to understand. Even if I write another subsets, do you see one thing? That, sir, phi is present in power set of S as well as in the power set of S. Apart from that, this element is present in power set of S as well as in the power set of S. So when we take the intersection, it will not only be phi, but this will be phi along with a set containing element 1. So got the idea that it is not necessary that power intersection of power set of S and power set of F S will always be phi. So it says always true. So in most of the cases, statement B will be true. In most of the cases, statement B will be true. But there are some cases, there are some scenarios in which statement B may also be false. Statement B may also be false. So this is a false statement. This is a false statement. Again, power set of S intersection S will be power set of S. It's absolutely rubbish. The power set of, this is S. This is S. This power set of S. If you take the intersection, it is saying that it will come out as power set of S. Come on, size of S will be smaller than size of power set of S. Therefore, even if it comes out as equal, then it will be same as set S, but it will not even be equal as same set S. Therefore, this statement is also false. S belongs to power set of S. Hey, come on. This is your set S. This is your set S. This set S belongs to power set of S, but it says that it does not belong to power set of S. No, the set S will always belong to power set of S, because S also will be a subset of S, and it will eventually become a member of power set of S, because power set of S is a set of all subsets of S. S is also a subset of itself, therefore S will also be a member of power set of S. So if it is S belongs to power set of S, it will be true, but this is false. This is false. So with respect to given question, there is no correct answer. Therefore, please make sure that if you come across this question ever while trying to solve the GATE previous year questions, then make sure that none of them is the correct answer. So don't get confused that, sir, I'm getting this and this answer, whereas some other answer is given in the answer queue or anywhere else. Okay, let's move ahead with the today's topic. So today we are going to discuss different types of set operations, that what are the set operations that can be performed, and the properties of set operation along with the different types of relation. So let's discuss the set operations. Sir, what are the various types of set operation? One is the complement of a set. Given a set, can you identify the complement? So please, the very first thing which you need to understand is, to determine the complement of a set, you will first require the universal set. Complement of a set will always be defined, no matter what. Complement of a set will always be defined with respect to universal set. Let's try to understand this. So complement of a set. So what are the different operations? Let me first name them, and then we'll discuss them one by one. So complement of a set. I hope that some of the things don't need any discussion, but I'll just give you an overview of those things. Union of two sets, intersection of two sets, set difference, I'll try to explain. Symmetric difference, I'll try to explain. Apart from that, for this two, I'll just give you the definition, and that will be all. So what do I mean by complement of a set? So the very first thing is that complement of a set is defined with respect to universal set. Defined with respect to universal set. Okay, so sir, what do I mean by the complement? For a set A, how do we define a complement? Sir, a complement will be a set of elements X. A complement will be a set of element X such that, sir, look at this. Sir, if I just give you an example first, let's assume that this is my universal set. Universal set is 1, 2, 3, 4, 5. Okay. Apart from that, I define a set A, which is nothing but 1, 3, 4. 1, 3, 4. So what will be A complement? Sir, A complement is the set of elements which are present in the universal set but not present in the actual set A. So what are the elements which are present in the universal set but not present in set A? So those elements are 2 and 5. Those elements are 2 and 5. So what is A complement? Sir, A complement is a set of element X such that X will eventually belong to your universal set. This is your universal set. And at the same time, X should not belong to set A. Obviously, all the elements will belong to universal set, but we only need to choose the elements which are not present in A. So when you look at 1, X1 belongs to universal set, but this another condition that X1 should not belong to set A is false. So this becomes false. So and will eventually become false, and X, that is X equals to 1, will not become a part of the complement. So this is the simple logic. 2 is present in the universal set and not present in the set A. Therefore, 2 will be a part of A complement. Okay, let's look at this, that we can also represent the sets in the form of Venn diagram. So let's assume if this is your universal set and this is some set A, then what will be the complement? How do we denote the complement? So the elements which are part, that is the elements which are in this yellow color shaded region, are the elements which actually belong to the universal set but do not belong to the set A. So this yellow color shaded region will eventually represent complement of set A in terms of Venn diagram. Okay, that's the basic thing. Next is union of two sets. Sir, how do we define the union of two sets? So let A and B are two sets. Let A and B are sets. So how do we define the union of A with B. Let's first try to understand using the Venn diagram. First try to understand the Venn. Let's assume that this is your universal set and we have two subsets of this universal set. One is set A, this is your set A. Another is set B. There may be some intersecting portion in set A and set B. So it's not necessary that all the elements of set A and set B will be distinct. There may be same elements in set A and in set B. So how do we define A union B? Sir, A union B eventually correspond to the elements which are part of either A or B. So even the elements which are common between A and B will also be part of A union B. So if I take this red color shaded region, then it will eventually correspond to A union. This is nothing but this red color shaded region is your A. So what do I mean by A union? Sir, A union B is nothing but a set of element X such that X belongs to A or. So if the element X belongs to any of these two sets A or B, that is, this or should return true. Whenever this or is returned true, for whichever element this or returns true, that element will be a part of your union A union B, right? So either X should belong to A or X should belong to. Clear? So the elements, so if I just give you an example fast, let's assume A equals to 1, 2, 3 and A equals to 2, 3, 4. So what will be A union B? So the elements which are part of either A or B, 1 is part of A, 2 is part of A, 3 is part of A and 4 is part of B. So elements which are in the union of A and B will be all the elements of set A and B. Anyway, the elements will not be repeated because it is the definition of a set. So you will not write 2 times, you will not write 2 times, you will not write 3 2 times, etc. Okay, let's move to the next definition, that is intersection. Sir, how do we define the intersection? There is another thing which is important from the intersection point of view. So I'll discuss that. Let A and B are two sets. Yeah, fine. Sir, how do we denote the intersection? This is the symbol for intersection. Let's try to understand the intersection using the Venn diagram. So what do we mean by intersection? So let's assume that this is your universal set. This is some set A and this is set B, or B and this is your set A. Sir, what do we mean by intersection? So the elements which are common to A as well as the elements which are common to set A and set B will correspond to A intersection B. That is, the elements which are present in A as well as in set B. So let's look at this. So what will be A intersection B? So it will be a set of element X such that X belongs to A and so this and should return true. That means X should be a part of set A as well as X should be a part of set B. Yeah. So again, same example, if I take what? A equals to 1, 2, 3, B equals to 2, 3, 4. What will be A intersection B? Sir, A intersection B will be 2 and 3. These are the elements which are common to set A and set B. Okay. One important thing which is related to intersection of two sets is that if A intersection B equals to 5, that is, if there is no common element, between the sets A and B, then A and B are called disjoint sets. So if you ever see this term disjoint, then you must understand that, okay, if two sets are disjoint, it means there is nothing in common in between sets. So then A and B are called disjoint sets. So whenever you have two disjoint sets in the Venn diagram, they will look like this, that there is nothing in common. So a universal set, this is your set A. If two sets are disjoint, then there will be nothing in common. So, is there any common element? No, sir. A intersection B is actually 5. A intersection B is actually 5. Okay, sir. This is the next definition is set difference. So what do we mean by set difference? This what you need to understand is that with respect to union is commutative. What does it mean? A union B will be equals to B union, that because the definition of set says that it is unordered collection. Therefore, whether you take A union B or B union A, elements will be same. The ordering may be different. Ordering may be different, but the overall idea is that set is unordered collection. Therefore, A union B will be same as B union A. Similarly, A intersection B will be same as B intersection A. Sir, why are we discussing? Because the set difference is a different type of operation which is not commutative. Let us just try to understand what is A minus B. Let A and B are two sets. If you try to understand the definition of A minus B intuitively, then A minus B is the set of elements which are present in A, or are present in A. So they must be in set A, but not present in set B. But not present in set B. So let's try to understand. This is your Venn diagram. If you have two sets, this is your set A and this is your set B. Then these elements which are present in this yellow color region are basically present in set A as well as in set B. So they cannot be part of A minus B, because in A minus B the elements which are allowed are should be present in set A, but they should not be present in set B. If there are some elements which are present in A as well as in set B, then they will not be member of A minus B. In A minus B, this is your A minus B. I'll define it in a different way. Just 1 minute. So let me write the set builder form for A minus B. So what is A minus B? A minus B is a set of element X such that, sir, what property should hold? X should belong to A. X should be a member of A, and at the same time, the same X should not belong to B. If X does not belong to A, this itself is false. Therefore, it will not be a member of A minus B. If it belongs to A and it also belongs to B, so if it belongs to B, the second condition will become false and will return false. It will not be a member of A minus B. But if there is any element which is a part of set A but not part of set B, then it will eventually be a part of A minus B. Okay, so this is A minus B. Please look at this carefully. Let's use this blue color. So if I take this right side region, then this is what? So these are the elements. This blue color elements are the elements which are present in set B but not present in set A. Therefore, it will represent B minus A. Do you see that set of A minus B is different? Set of B minus A is different. So you can actually say that A minus B is not equals to, so in general, A minus B is not equals to B minus A. When exactly A minus B will be equals to B minus A? Sir, A minus B will be equals to B minus A only when A is equals to B. A minus B equals to B minus A only if A is. In that case, what will be value of A minus B? Sir, A minus B will come out as phi. A minus B will come out as phi. Okay, sir, can we represent A minus B in a different form? So let's try to understand that what is A minus B. If I take all the elements of set A, out of those elements, if we subtract the element which are present in the intersection of A and B, so can I say A minus A intersection B? So elements of set A apart from the elements which are common to A and B will be part of A minus B. So that's another way of representing this. Perfectly fine, there's no problem with that. So there are different ways in which we can represent uh, just 1 minute. A minus B, not A and sorry, thank God. A minus B. So the elements which are present in A minus B are the elements of set A except the elements which are common to A and B. Okay, so this is set difference. Next one is symmetric difference. So what do we mean by symmetric difference? So this difference is symmetric. So please try to understand what is symmetric difference. So first of all, how do we denote this? Most of the things are known, but set difference is generally denoted by using this symbol delta. They may use some other symbol, but they will define it if they are using any other symbol. So let A and B are two sets. A symmetric difference B is the set of elements that are present either in A or in set B, but not common to A and B. That means the elements which are present in A or in B but should not be present in both these sets. So you'll eventually realize that if this is your Venn diagram, this is your set A, the set B, then what are the elements which are present in set? So these are the elements which are present only in set A. So either in A or in B, but they should not be present. They should not be present in both these sets. That is, they should not be common. So we actually need to skip or avoid the elements which are present the intersection of A and B. So how can we define the set in the set builder form? So A symmetric difference B is X such that X belongs to A or X belongs to B. So X should belong to A or X should belong to B, but where X must not belong to A intersection. Where X must not belong to A intersection. So please remember that A symmetric difference with B is equals to B symmetric difference with A. It means that the symmetric difference operation is a commutative operation. No matter in what order you perform the operation, you will get the same result. Okay. Sir, what else? Sir, what is asymmetric difference B? If we take all the elements of A and B, apart from that, if we subtract the elements which are common to A and B, then we will get asymmetric difference B. Can I say that asymmetric difference B is nothing but the elements which are present in A union B. So the elements of A union B, out of the elements of A union B, if we subtract the elements which are common to A and B, then we'll eventually get A symmetric difference with B. Clear? So these are the different types of operations. Let's try to understand the properties of operation which will hold true. So please, properties of set operation with respect to union and intersection. We are not saying that all the operations will follow this property, but we are explicitly denoting that this properties will hold true with respect to set union and set intersection. So what does it say? So if first one is idempotent law, that is if you perform the union of same set, then you will get the same set. If you perform the intersection of same set, that is A union with A will be A intersection with A will be A. That's fine. Identity law, sir, what does it say? Identity. If you perform, if you have a set A, if you union phi with that, sir, what will we get? Sir, phi is nothing. So even if we add nothing extra in the set A, then we will be left with set A only. So A union with A will be A union with phi will be A intersection with the universal set. So all the elements of A will also be the part of universal set. So ultimately when you perform the intersection, you will get the same set A. Clear? So this is the identity law. Okay, then we have domination law. So these are two opposite things. So if you perform the union of A with phi, you will get A. But if you perform the intersection of A with phi, then you will get phi. this domination law, that in this case phi will dominate. In case of intersection, phi will dominate. In case of union, universal set will dominate. So A intersection phi will be phi. A union with universal set will be universal set. I mean, I hope if you have any doubt in this particular things, please ask in the comment box, because otherwise it will be just the wastage of time. So I'll not waste your time. So complementation. So what do we mean by complementation? Okay, we just explained one simple thing, that this is your universal set. This is your set A. Let's assume the elements of set A are this blue color shaded region. And what will be complement? The complement of A will be this red color shaded region. Now my question is, if we union all this blue color elements and this red color elements, then what will we get? The blue color element plus red color element will eventually be all the elements of the universal set. So if you take the union of set A with its complement, then you will get the universal set. Clear? Similarly, there are no common element in this red color shaded region and blue color shaded region. So if you take the intersection of set A with its complement, you will get phi. There is nothing in common between the set and its complement. There will never be anything in common between the set and its complement. Okay, double complementation, that is, if you take the complement, then you will get this red color region. If you take the complement of this red color region, you will again get the same set, right? So if you perform the double complementation on any set, then you will get the same set. So complement of A will be A only. Complement of A will be A only. Next, commutative. So we have already discussed A union B is B union A intersection B is B intersection A. What is associative? In what order you perform the union of three sets is not important. The ultimate result will be same. That is, if you first perform the union of elements of B and C, and then you perform the union of the result with the element of set A, or if you perform the union of A and B first, then you perform the union of result with the elements of set C, then result will be same. Associative. I mean, that means you can change the order. It means you can change the order. You can write some other things also, because they are commutative. So you can write A union B union C will be same as B union A union C. Whatever. I mean, commutative, associative, in whatever order you perform the operation, the result will be same. Apart from that, one important property is the distributive property. No, it's not here yet. Yeah, on the next slide. Anyway, don't worry. So what do we mean by absorption law? Absorption law. So please try to understand this carefully. Most of the time student will eventually prompt in this. So this is your set A. This is A intersection B. My question is, whatever is present in this A intersection B cannot have any extra element apart from the elements of set A, because A intersection B will be a set in which the elements will be the elements which are present in A intersection B are actually the elements which are common to A and B. That means all the elements which are present in A intersection B are also present in set A. All the elements which are present in A intersection B are also present in set A. So let's assume A is equals to 1, 2, 3, 4. 1, 2, 3, 4. Now my question is, let's assume B is 3, 5, 6. B is 3, 5, 6. So what is A intersection B? Sir, A intersection B will be 3. So the element which is present in A intersection B is already present in set A. So if you perform the union of A with this A intersection B, then you are not going to get any extra element, because all the elements of A intersection B are already present in set A. So union is not going to add any extra element. That means A intersection B will be absorbed in set A, because A intersection B does not contain any extra element apart from the elements of set A. So no element will be present in A intersection P such that it is not present in set A. So this is one. Apart from that, same thing can be defined with respect to union. So if you take A union B, then in A union B, all the elements of set A as well as all the elements of set B will be present. All the elements of set A as well as all the elements of set B will be present. If you perform the intersection with set A, then ultimately you will get all the elements of set A, because all the elements of set A are present in A union B. So effective result will be A. from the naming sake, if somebody asks you that what is the absorption law, you must remember this. Otherwise, you can eventually check the concept. You can apply some logic and you will be able to check whether these two are equal or not. But just for the sake of uh, giving the answer in the form of name, if somebody asks you that what do you mean by absorption law, you must know that this is the absorption law. Otherwise, from the gate point of view, it's okay. Now, what is De Morgan law? So, when we perform the complement of the union, then individual set will be complemented and union will get converted into intersection. Similarly, if we perform the complement of the intersection of two sets, then these sets will get complemented and intersection will get converted into union, right? So when we perform the complement of A union B, then this will become A complement, set will get complemented, B complement, set will get complemented, and union will become intersection. Similarly, A will become A in complement, B will become B complement, and intersection will become. So these are the simple logics, nothing more than that. So you all know all this concept from the digital logic also, because we need all these rules in the Boolean algebra. We use all these rules in the Boolean algebra. The same distributive property is also valid for Boolean algebra. What is distributive property? If you perform, so it's tricky, you just, I mean, whatever way suits you, you just need to remember this. And this is most important because most of the time when somebody asks you to simplify a given expression, this property will be very useful, because most of the time people are not able to visualize in terms of distributive property. So please note down this property if you don't already know this, and revise it as many times as you can, so that you will be comfortable with this operation, that how exactly the union will be distributed across the intersection, and how exactly intersection will be distributed across the union, right? So if you have A union, so whatever is this within the bracket will eventually become the common point of two sets. This is union, so it will become the common point of these two sets. So it will become A union B and A union C, A union B and A union C. One will be A union B, another will be A union C, and finally you will have the intersection of these two, A and, okay. If you want to remember this in form of Boolean algebra, then this will be very easy. A video lectures first already posted है बेटा, जाकर के देखो, first is already available on the channel. Okay, come on. So if you want to visualize this in the form of Boolean algebra, then what can you do, sir? You can eventually think of this union as a plus, and you can think of this intersection as multiplication, or and or, and or. Yeah. So this will eventually become what? So it will become A plus C. So what is this, sir? It will be plus B plus C. Similarly, you have A dot B plus C, then this will be A dot B dot C. So it's okay. If you simply replace union by plus and by dot, you will get the same thing. Nothing different from Boolean algebra, but in terms of union and intersection, this will look like this. No difference. Okay. So we have seen all the different types of operations which can be performed on two or more sets, and we have also seen that what are the different properties which will hold true for the union and intersection. Yeah. Please make sure that you revise all these properties once or twice before you try to simplify any given expression. So what's the use of this property? So given an expression, if somebody asks you that what will be the simplified form for that particular expression, then while simplifying the given expression, all these properties will be very useful. Apart from that, when we are trying to solve the questions that is being asked, this Venn diagram will be very helpful. Venn diagrams that we discuss will be very helpful in analyzing the output of a given question. Okay, let's move to the next concept, that is Cartesian product. What do we mean by Cartesian product? Come on. Let A and B are two sets So basically, this is the beginning of the concept of relation. This is the beginning of the concept of relation. If you want to understand the relations, first of all, you must understand the concept of Cartesian product, because relations are nothing but the subset of Cartesian product that we'll define in a while. So let A and B are two sets. Are two sets. Cartesian product of A and B is denoted by Cartesian of A and is denoted by A cross B, and it is defined as, this is very important, and it is defined as, how do we define the Cartesian product? The Cartesian product A cross B is a set, but what will be the elements of this set? The element of this set will be the order pairs. What is this? So this is the order pair. Please, when I say order pair, then order is important. Order is important. Order pair A dot B is not equals to order pair B dot A. So these two are not the same thing. Clear? So what is A cross B? A cross B is an order pair in which the first element will be A, second element will be set B. What type of order pair is this? So this is an order pair such that the first element of the order pair, that is A, will belong to the first set, A will belong to set A, and the second element of the order pair, that is B, will belong to second set, that is B will belong to set B. Just 1 minute. Sir, if we have this set A, and if we have the elements A1, A2, we have set B, and let's assume there are two elements, 1 and B2, then what is A cross B? Sir, A cross B will be, sir, A1 will relate with B1, A1, 1, I would rather say 1, oh, then we'll have A2, 1. If I try to represent this Cartesian product pictorially, then what will happen? Sir, A1 will relate with B1, A1 will relate with B2. Similarly, A2 will relate with B1, A2 will relate with B2, A3 will relate with B1, and A3 will relate with B2. So what happens in the Cartesian product? In the Cartesian product, A cross B, in the Cartesian product A cross B, every element of set A will relate with every element of set B. Okay, so just note down, in Cartesian product A cross B, in Cartesian product A cross B, every element of set A relates with every element of set B. I hope you understand that this will be, oh come on, sorry. This will be the set of Cartesian product of A and B. Now please try to understand, if I perform A cross B, then the first element will be from set A and the second element will be from set B. That is, it will look like this. But if we perform B cross A, then what will be B cross A? So, what will be B cross A? In B cross A, the first element will be from set B and the second element will be from set A. So you will have B1, A1, B1, B2, B1, B3. Similarly, B2, B1, B2 combined with B2 combined with A3. And as we know, A1 B1 is not same as B1 A1. Therefore, A cross B is not equals to B cross A. A cross B is not equals to B cross A. So please just note down Cartesian product, same topic, Cartesian product. In general, A cross B is not equals to B cross A. Is there any case when A cross B can be equals to B cross A? Yes, sir. A cross B may be equals to B cross A if A is equals to B, or a specific case, or if at least one of these two set is an empty set. If any one of these two set is an empty set, then the Cartesian product will also be an empty set. Cartesian product will also be an empty set. So in general, A cross B is not equals to B cross A. What can we say? If A cross B is equals to B cross A, if A cross B equals to B cross A, then either A is equals to B, or at least one of two sets is an empty set. One of these two sets, A or B, will be an empty set. Clear? This A cross B equals to B. Anyway, next thing. What set is related to cardinality? So one complete order pair will be treated as one element, sir. This is one element of A cross B, this is another element of A cross B, this is another element of A cross B. So how many elements in this A cross B? Sir, every element of set A will relate with every element of set B. So if I say that the cardinality of set A is M and cardinality of set B is N, then each one of this M element will relate with each one of n elements. Therefore, total number of order pairs will be M into N. So that's another thing which you can note down. If mod A equals to B, if mod A equals to M and mod B equals to N, then what is the cardinality of A cross B? So cardinality of A cross B will be nothing but cardinality of set A to cardinality of set B, that is M into N. Each one of this M element will relate with each one of N elements. Each one of M element of set A will relate with each one of N element of. Now, please try to understand what happened in the Cartesian product. Sir, in the Cartesian product, every element of set A relate with every element of set B. Now, my question is, if we want to define the relation, then in a relation, it is not necessary. In a random relation, it is not necessary that every element of set A relates with every element of set B. But if we are defining a relation from set A to set B, if we are defining a relation from set A to set B, then a relation from set A to set B will eventually be a subset of A cross B, because when you say from A to B, means how exactly the element of set A are related to the element of set B. We are not saying that how elements of B are related to set A. We are saying how exactly the element of set A are related to set B. So the ordering will be important. It will say whether elements of A are related to B or element of B are related to A. That's what we are trying to understand. The next thing, that is relation. So what is a relation? A relation from set A to set B defines that how exactly the elements of set A relates with elements of set B. Okay. Please, first of all, before I go to the next definition, let's try to understand that this is my set A, A1, A2. This is my set B. So it's not necessary that in a random relation, all the elements of set A relates with all the elements of set B. It may be possible that A1 relates with B1, A2 relates with B1 as well as B2, but A3 is not related with any element. So this relation will only contain the order pair that, okay, A1 relates with B2. It defines that, okay, A1 is an element in set A which relates with B2. A2 will relate with B1 and A2 will relate with B2 also, but there is no other relationship from the elements of set A to elements of set B. Do you realize that this relation from A to B, this relation from A to B is a subset of A cross B? All these order pairs are also present in A cross B. A1, B2 is present. A2, B1 is present, A2, B2 is present. So can I say that if we define any relation from A to B, then it will be a subset of A cross B. How exactly the elements of set A relates with elements of set B will eventually be a subset of A cross B, because in A cross B, every element of set A relates with every element of set B. Clear? So if there is, don't want to make things complicated. Anyway, so every relation from set A to set B is a subset of A cross B. Every relation from set A to set B is a subset of A cross B. Whatever order pairs appears in the relation will be from A cross B. Clear? Okay. Not a. Let's go ahead and try to understand next thing. So, let mod A equals to M and mod B equals to N. Then how many relations are possible from set A to set B? Then number of relations possible from set A to set B. Sir, how many relations will be possible? You just need to understand. I just give you an intuition that every subset of A cross B will be a relation. So how many distinct relations are possible? So the number of distinct relations will be same as number of distinct subsets of A cross B. Will be same. So number of relations possible from A to B will be equal to the number of subsets of A cross B. Now please tell me, what is the number of subsets of A cross B? Number of subsets of A cross B will be, number of subsets of A cross B will be nothing but 2 raised power cardinality of A cross B, because that's how we define the number of subsets. How many subsets of set A? Number of subsets of set A will be 2 raised power number of elements in set A. So similarly, number of subsets of A cross B will be nothing but 2 raised power number of elements in A cross B. Sir, we have just defined the value of cardinality of A cross B. It is nothing but cardinality of A into cardinality of B. So basically, it's nothing but 2 raised power cardinality of A is M. Number of elements in set A are M. Number of elements in set B are N. So, do you realize that one of the subset of A cross B is an empty set? One of the subset of A cross B is an empty set, which is called an empty relation. So don't think that, sir, empty set is not a relation. Empty set is also a relation. A special name is given to that relation. It is known as empty relation. So please note down, one of the subset one of the subset of A cross B is an empty set. It is also one of the subset of A cross B is an empty set. This empty subset of A cross B is also a relation from A to B. This is called empty relation, and it is called empty relation from A to B. Sir, come on. There is also an information. There is also an information that no element of set A relates with any element of set B. So there is no relationship from the element of set A to set B. So it's called empty. Clear. Okay, so these are certain things you have understood. Now let's move to the different types of relation. So we have defined the relation, that what exactly we mean by relation. A relation from A to B, will be called, a relation from A to B will be a subset of A cross B. Let's have one more note. If I just try to define a relation from A to A, so it may also be possible that both these sets are same. So note, a relation from set A to set a relation from set A to set A is called a relation. So this is basically a relation on the same set. Therefore, it is called a relation on set A. A relation from set A to set A is called a relation on set A. Okay. Next, if mod A is equals to n, then number of relations possible on set A will be what? Number of relations possible on set A. Sir, this is from A to A. That means it will be a Cartesian product. It will be a subset of Cartesian product A cross A. It will be nothing but 2 raised power mod A into mod A, which will be 2 power n. Mod A into mod A will be n square. Clear? So, if a relation is from set A to set A itself, that will be called a relation on set A. This is very important because most of the questions or most of the relations are defined on the same set. Most of the relations are defined on the same set. Okay, let me just give you an example that, it's not an example, you just need to understand this thing in the form of a matrix. So let's assume let A equals to 1, 2, 3 up to n. Now my question is, sir, what will be A cross A? Sir, A cross A will be a set in which every element of set A will relate with every element of set A itself. So it will be like the element 1 will relate with 1, element 1 will relate with 2, element 1 will relate with 3, and so on. 1 will also relate with n. Clear? Similarly, element 2 will also relate with 1, element 2 will also relate with, element 2 will relate with 3 as well, up to 2 will relate. Similarly, 3 relate with 1, 3, 3 will relate with 3, and so on. 3 will relate with n as well. So, up to n, the element n will relate with 1, element n will relate with element n relate with 3, so on, n will also relate with n. I hope you understand. So how many order pairs are there, sir? Overall, n square order pairs. Overall, n square order pairs in A cross A. Therefore, how many subsets are possible if the cardinality is n square, 2 raised power n square? So 2 raised power n square subsets are possible, and each one of those 2 raised power n square subset will represent a relation on set A. So this matrix is very important. Do you visualize one thing? Do you visualize one thing? That if I think of this particular thing as a matrix, then these elements are actually on the diagonal of this matrix. These elements are actually on the diagonal of this matrix. Yeah. So just for the visualization purpose, so that you understand the things in with more clarity. So it's okay that if A is any set of cardinality n, and if we define A cross A, then each element of set A will relate with every other element of set A, and ultimately it will look like a matrix of size n cross n. It will look like a matrix of size n cross n, in which there will be n square order pairs, and each one of each subset of A cross A will represent a relation on set A, and if there are n square elements, then 2 raised power n square subsets will be there, and each one of those 2 raised power n square subset will represent a relation on set A. That's it. Having said that, we will try to define the different types of relations. Okay, so the very first relation is diagonal relation. I hope you understand the meaning, that this definition of diagonal relation will be quite easy to understand once we have seen that matrix representation. So, what is diagonal relation? Diagonal relation is a relation which contains all the order pairs of that all the diagonal order pairs of that particular matrix. No other element is allowed. All the diagonal order pairs should be present, and the remaining order pairs are known as non-diagonal order pairs. So let's try to understand. For the purpose of explaining the concept, I will name them as diagonal order pairs, and every other order pair will be known as non-diagonal order pair. Right? So these are what? These are the diagonal order pairs. And this are nothing but non-diagonal order pair. Okay, sir. Let's move further. So let me first define the different types of relations first. So diagonal relation will be one relation: reflexive, irreflexive, symmetric, antisymmetric, asymmetric, transitive relation. Then these 7 relations are defined on set A. Defined on same set. So these two definitions, relation can be defined from any set A to any other set B. Same or different, we don't worry about that. Same or this you understand by the name itself that this is the composite of two relations. Just like we define the composite function, similarly we can define the composite relation. Anyway, so let's begin with the diagonal relation. The diagonal relation on set A, how do we denote this? Diagonal relation on set A is denoted by delta A. Sir, it is also known as identity relation. Also known as identity. So because it is known as identity relation, therefore some authors may define it like IA, that is identity relation on set A. So whatever, I mean, up to the notation, it doesn't matter. Okay, so it is denoted by delta A or IA, and it is defined as, come on, and it is defined as, how do we define the diagonal relation on delta A? So how do we define the diagonal relation on set A? So diagonal relation on set A is a set of order pair x comma x such that x belongs to set A. So this is the definition of a set. Please, please, please. This is the definition of a set. What does it mean? If it is the definition of a set, then this set can contain only this type of element, and it should contain all the elements which satisfy this condition. No other element should be present, no element should be missing. No other element should be present, no element should be missing, because this is the definition. It is the notation in the set builder form. So all the elements which are satisfying this predicate must be present in this delta A. So let's try to understand with the help of an example. So if I have A equals to 1, 2, 3. So let's assume R1. If I write 1, 1, 2, 2, 3, 3. 1, 1, 2, 2, 3, 3. So all diagonal order pairs are present. All diagonal order pairs are present. Yes. So it is diagonal relation. This is a diagonal relation. If I take another example, please, let's assume if I take R2 on the same set, if I take only two order pairs, 1, 1, 2, 2, and we do not take 3, 3, then is it a diagonal relation also? Is it also a diagonal relation on set A? No, sir. It is the definition of a set, that is, for all the x which satisfy this constraint, that if x belongs to A, then order pair x, h should be present in the relation. So the idea is, because 3, 3 is not present in R2, so as 3, 3 does not belong to R2, therefore R2 is not equals to diagonal relation on set A. R2 is not a diagonal relation on set A. Okay, sir. Next, sir, can we have any extra element apart from all the diagonal order pairs? So look at this, R3, 1, 1, 2, 2, 3, 3. It's perfectly fine. Up to this point of time, it's okay. But the moment you add any other element, let's assume if I add 1, 2, then is it a diagonal relation on set A? No, sir, because non-diagonal order pair cannot be present. Non-diagonal order pair cannot be present, not equals to delta A, because 1, 2 cannot belong to delta A. So the only thing is, only and all the diagonal order pairs must be present in the relation for it to be called a diagonal relation on set A. For it to be called a diagonal relation on set A. Clear? Okay, so that's one thing. Let's move to the next definition, which is a reflexive relation. So what do we mean by reflexive relation? Come on. Now, while we will understand, and we will also understand the basic difference between diagonal relation and reflexive relation. What is reflexive relation? Okay. A relation R on set a relation, whatever relation, a relation R on set A is called a reflexive relation. Is called a reflexive relation, and only if and only if, come on, this is A relates to A for all A belonging to set A. This notation is what you need to understand. What does it say? It says element A relates with A completely. Just try to understand. A relates with A. In the other language or in the other notation, it can be written as that is that A relates with A. A relates with A. So please look at this. Okay. Sir, what does it say? So 3 relates with A. 1 relates with 1. 3 relates with 1. So when I say A relates with A, it means when I say A relates with A, then it means order pair A comma A should belong to relation R. A relates with A with respect to, or more clearly, A relates with A with respect to relation R. With respect to relation R. That means A comma A should be present in relation R. A comma A should be present in relation R for all the elements A belonging to set A. So, sir, what is the difference? Don't you think that this looks like exactly same as a diagonal relation? Sir, in diagonal relation, it is the definition of the set. In diagonal relation, it is the definition of set, whereas this is the constraint on the relation. What does it mean? If and only if, uh, sorry, only if, A relates with A for all A belonging to set A. Come on. So, what does it say? That for all the elements A comma A should be present in the relation R, but we are not commenting whether other things can be present or not. So, it is just a constraint on the relation. Okay, in a while it will be more clear. I'll give you the example. Now my question is, if I write a relation R1, 1, 1, 2, 2, 3, 3. Is it a reflexive relation? Is it a reflexive relation? So the constraint is that for all the elements belonging to set A, the element A should relate with A. Yes, sir. All diagonal order pairs are present in the relation. Therefore, it is a reflexive relation. So it is also the diagonal relation. It is also the diagonal relation. So can I say it is reflexive as well as diagonal relation? Now, what you need to understand is every diagonal relation is reflexive. Every diagonal relation is reflexive. But if a relation is reflexive, is it necessary for it to be diagonal? Let's check. Sir, relation R2. Please tell me, if I have all the order pairs 3, 3, if I write any other order pair, so please tell me, the only constraint on the relation is that for all the elements of set A, the element should relate with itself. That means all diagonal order pairs should be present. Apart from that, some other thing may or may not be present. It's not defined. That means they may be present in the relation, they may not be present in the relation, but for all diagonal order pair, but all the diagonal order pairs must be present in the relation. So please tell me, is it reflexive? Yes, sir, it is reflexive because all diagonal order pairs are present. But is it diagonal? No, sir, because no non-diagonal order pair can be present in the diagonal relation. So it is reflexive, but not a diagonal relation. Can I say every diagonal relation on set A every diagonal relation on set A is every diagonal relation on set A is reflexive relation is a reflexive relation on set A. But every reflexive relation on set A need not be the diagonal relation not be the diagonal relation on set. Okay. Now let's go back and try to look at the example which is not a reflexive relation. Please tell me, if I have some of the order diagonal order pairs, but if we do not have others, then will it be reflexive? No, sir. 3 comma 3 does not belong to. 3 comma 3 is not present in R3, therefore not reflexive. Because 3 comma 3 does not belong to R3. Yeah. So if any of the diagonal order pair is missing, it cannot be reflexive. For relation to be reflexive, all the diagonal order pair must be present. Apart from diagonal order pairs, some non-diagonal order pairs may or may not be present. There's no restriction on the presence or absence of the non-diagonal order pair, but all diagonal order pair must be present. In the diagonal relation, the only thing that is allowed is the diagonal order pairs. None of the non-diagonal order pairs should be present in a diagonal relation, right? So can I say that diagonal relation is the smallest reflexive relation? If you remove anything from the diagonal relation, it cannot be reflexive. So diagonal relation is the smallest reflexive relation, and the largest reflexive relation on set A will be A cross A. Largest reflexive relation on set A will be A cross A. Now my question is, how many? So I understand that the time is limited, so we need to cover most of the things, so I'll not be able to give you the proof of this particular thing, but you can actually explore it at other places, or in some upcoming sessions we'll discuss this particular things in more detail. What, like, if mod A is equals to n, that is the size of set A is n, then mod A equals to n, then number of reflexive relations possible on set A. How many reflexive relations are possible on set A? I'll just give you the intuition. What, sir? The very first thing is that out of n diagonal order pairs, if I tell you that how many diagonal order pairs are there in this diagram, sir, there are n diagonal order pairs. How many diagonal order pairs, sir? Diagonal order pairs. So if I write number of diagonal order pairs are how many? So there will be exactly n diagonal order pairs, and these are the non-diagonal order pairs. If I ask you, number of non-diagonal order pairs will be how many? Sir, overall n square order pairs are there. So out of n square, exactly n are diagonal. Remaining n square minus n are non-diagonal order pairs. So if somebody asks me that, sir, how many reflexive relations are possible on set A, then the very first intuition will be that, sir, we need to choose all n diagonal order pairs out of n diagonal order pairs, and for remaining n square minus n elements, we have two choices for each element. We can choose that element or we can leave that element. There is no restriction on those non-diagonal order pairs. So for n square minus n non-diagonal order pairs, we have two choices for each non-diagonal order pair. Leave it or take it. Leave it or take it. Leave it or take it. Clear? Or otherwise, you can sir, NCN, that is, you need to choose all diagonal order pairs, and out of n square minus n non-diagonal order pair, you can choose 0. Out of n square minus n, you can choose 1, up to out of n square minus n, you can choose all n square minus n. So either you can choose 0 out of those non-diagonal, 1 out of those non-diagonal, 2 out of those non-diagonal. You can choose all out of those n square minus n non-diagonal. So nc0 plus nc1 plus nc2 up to ncn is 2 raised power n. Similarly, n square minus nc0, n square minus nc1 up to n square minus nc, n square minus 1 will be 2 raised power n square minus n. Clear? So So what will be the final answer? The final answer, that is the number of, sir, NCN will be 1. NCN will be 1 into 2 raised power n square minus n. Therefore, the final answer, that is the number of reflexive relations possible on set A, where cardinality of set A is n, will be 2 raised power n square minus. Done. So this is all about reflexive. Let's try to understand irreflexive. Is irreflexive. Sir, so is it the case that the relation which is not reflexive is irreflexive? No, not necessarily. So please try to understand irreflexive. What? A relation R on set a relation R on set A is called irreflexive relation. Called irreflexive relation only if, what is the condition? Opposite. Only if A does not relate with A for all A belonging to set A. That is, A does not relate, that means the order pair A comma A should not belong to relation R for all A belonging to set A. For any element, if this belongs, then this for all will return false. So for none of the element of set A, for none of the element of set A comma A should belong to R. Diagonal order pairs are not allowed. Diagonal order pairs are not allowed in the reflexive. That is, if simply try to understand this, then what does it say? That is, diagonal order pairs are not allowed in reflexive relation. Yeah, okay. Let's do some other things. Example. Equals to 1 to 3. What? Equals to 1 to 3. If I have a relation, please tell me. If I have 1 1, 1 2, 2 1, is it reflexive? No, sir. Not reflexive. Obviously not reflexive because 2 comma 2 and 3 comma 3 are not present. Is it irreflexive? 1 comma 1 belongs to R1. Therefore, not irreflexive also. 1 comma 1 belongs to R1. Therefore, not irreflexive because diagonal order pair cannot be present. If any, so can I actually say this relation R1 is neither reflexive nor irreflexive? Neither reflexive nor irreflexive. So that's a known fact that if any of the diagonal order pair is present, it can never be irreflexive. Similarly, sir, the simplest subset of A cross A, the simplest subset of A cross A is the empty set. Please tell me, empty set is a irreflexive relation or not? Yes, sir. The only condition is that the diagonal order pair must not be present. For any other element, there is no condition. For any other order pair, there is no condition. Therefore, can I say it is the smallest irreflexive relation? It is the smallest irreflexive relation on set A. If you take any set A, then empty relation will be the smallest irreflexive relation on that set. Come on, sir, R3. arithmetic 1, 2, 2, 1, 3, 2. That's it, 3, 2. Please tell me, is it irreflexive? Yes, sir. None of the diagonal order pair is present in R3. None of the diagonal order pair is present. R3. Therefore, 3 is irreflexive relation. R3 irreflexive relation, R1 not irreflexive, R2 not reflexive. Now, if I ask you how many irreflexive relations are possible, let mod A equals to n. Then number of irreflexive relations possible on set A. Come on, I hope if you have understood the definition for irreflexive relation and if you have understood that how did we count the number of reflexive relation, you know the answer for this as well. What? Sir, out of n diagonal order pair, none of them should be chosen. That is, choose 0 out of n diagonal order pairs, and for n square minus n non-diagonal order pairs, each one of those n square minus n non-diagonal order pairs will have two choices. So that's the thing, that in 0 way we can choose 1 to 2 raised power n square minus n. Final answer will be 2 raised power n square minus. Clear? So guys, we have discussed two relation, reflexive, irreflexive, but I believe that the time is limited and I have a paid class from just after a while, so I will not be able to continue with the remaining topics, but I'll try to include them in the next session. Don't worry, I'll try to include them in the next session. So the different types of relations: symmetric, antisymmetric, asymmetric, transitive, complement, inverse, and composite. These are what we need to discuss. That I'll include in the next session, or I'll conduct the next session only for them. Don't worry about that. So we have seen some of the relations: diagonal relation, reflexive relation, irreflexive relation. We have also seen how many reflexive relations and how many irreflexive relations are possible on a set A if the cardinality of set is n. So for any given cardinality, you will be able to identify the number of reflexive relations and number of irreflexive relations on set A. So we have seen set operations, we have understood the properties of set operation, we have seen the Cartesian product. So A cross B is not same as B cross A. A cross B is not equals to B cross A. If A cross B equals to B cross A, then either A is equals to B, or one of A or B is an empty set. In that particular case, A cross B will be equals to B cross A and the result will be phi. It will be an empty set. Clear? Now, sir, Cartesian product is basically the universal relation. Cartesian product is basically the universal relation. That is, if you want to define that how the elements of set A relates to elements of set B, then with respect to that, A cross B will be a universal relation. Makes sense that in A cross B, all possible pairing will be there, that how elements can relate, how elements of set A can relate with element of set B. But in a random relation, it is not necessary that all elements of set A relates with all elements of set B. So some elements of set A may relate with some elements of set B, and some may not relate with any element of set B. So that's the general relation, that it's generally what happens in the life, that some people may like some people, but they do not like other people, right? So that's the idea. But what actually will be a relation? Relation from A to B will be a subset of A cross B. So relation, we have understood the total number of relations possible from A to B will be same as number of subsets of A cross B, that is 2 raised power cardinality of A cross B. That is, yeah, that's enough. That if you take M into N, it's a different thing. Different types of relations. So we have understood 3 different types of relations: diagonal relation, reflexive relation, irreflexive relation. Remaining I'll complete in the next session. Okay, so that will be all for this particular session. Thank you very much for joining the session. See you tomorrow. Till then, take care, keep learning. Thank you very much, guys.